So good afternoon, everyone. So I'm Oliver, and I'm a master student at the Bernstein Center for Computational Neuroscience. And I've been working on my master thesis during the last few months, and I focused to find out where humans look in a visual scene. And I'm trying to build models that would predict where humans would look when they would explore a visual scene. And these are answers that I'm trying to find during this talk today. And yeah, so first of all, why do we need to care about this? So just imagine you want to find something in the supermarket. So you want to find a jar of pickles, and you are in the supermarket, and you're like really overwhelmed by all the massive retinal input that you receive, and your brain is very overwhelmed with all the data and like all the thousands of products, the like millions of pixels. So what do? Luckily, the brain has evolved into a system that's able to give you something like an attentional focus when you trying to solve a task. So in this case, since you know what you are looking for, with time, you will kind of focus on a specific part in your scene, which will guide you to fulfill your goal, actually. And I think you all know this feeling that when you are like trying to do something and you just have this like moment of focus that you only think about a certain part of your image at the moment. You try to like write a text, for example, and this is this attentional mechanism that I'm talking about. But there are two different things that contribute to attention. So there's like this top-down view on attention when that's kind of takes place when you try to solve a task, so you're very motivated to fulfill a goal, and this then drives you and motivates you to do something. But this is not always like dependent on your image itself. And this is why I'm going to talk about the second, more bottom-up approach. So it's these inherent features that the visual scene can have that then draw your attention to a certain part in the visual scene. And these are the things that I'm going to talk about. So how do we study human gaze? So what we can do is we can use eye tracking. So eye tracking is this technique that is able to record your eyes and reconstructs trajectories and fixations. And this gives you access to study where humans are looking at and to analyze this kind of data in the end. And there's like I'm just giving you like a brief summary on eye tracking research. So it started somehow in like the 50s and 60s, and like one of the pioneers in eye tracking was this person called Yarbus, and he kind of found out that when we explore a visual scene, what we are seeing is very task specific. So it's different when I'm asking you, please find out where this person on the left here came from, what's their background, to, for example, when you want to find out, what's the color of her eye, for example. So there's a dependence on where you looked on the task, and this was something new back then. It was very influential idea somehow in the field. And then later, psychologists and cognitive neuroscientists started to focus more on very basic mechanisms. So they tried to find out what does evoke a high attention in a certain region of a visual scene, and they kind of came up with these studies that looked like these oriented bars. And as you can see, they are all horizontal except for one, which is slightly oriented. And they found that it very reliably, when they would record eye tracking data from subjects, that most of the people, or almost all of them, would focus on this oriented stimuli. So this is somehow gives you an idea of what is important for the visual system such that you attend a certain region, because in this, there's like some information encoded in this orientation that's not there in the rest of the scene. So this is this idea of a local contrast being of importance here. But yeah, since we kind of also want to understand what humans process when they are in a like more natural setting, because these stimuli were very artificial, later people then again turned to more natural scenes. And for example, in the study by Judd and al., they used like a rather large data set, and I tracked 1,000 participants while they were viewing these images. And with that, we can now like look into models and similar things. But eye tracking is not only used in research, also industry has been very active in this domain. For example, if you would have designed a web page and you may want to make sure that the user is looking at the parts on your web page that you have that you want to highlight, then you can make like a check with an eye tracking device. So you can give the web page to some users, and you can like see the way they explore the scene and where they focus. And with that, you can really try to make sure that the user gets the content that you want the user to have. And also, very importantly, like it's used a lot in supermarket design. So companies are very interested in designing their selling spaces in a way such that they optimize the income, of course. So they're very interested that the consumer sees more pricey products or products of a certain brand, and with eye tracking, it's possible that they can check for this and maybe rearrange their products in a way that it's more optimal for their desires. So yeah, this is this. So what visual features could be of interest when we explore a visual scene? So there's been like a lot of different concepts that were proposed in the past. So one very intuitive idea. So this is the image that I'm going to use as a sample and to guide you through the different concepts. So color contrast is believed to kind of draw like human gaze somehow, because at locations where there is like a change in color, there seems to be a region where something interesting is happening, or where you should be alarmed, or like, yeah, I think it's quite intuitive. Then a second, another very low-level concept is orientation contrast. I think it's also already motivated with the oriented bar before, but also here. So at locations where the orientation or like the edges in an image somehow change, these are regions that the visual system might be interested in, because like all complex shapes are somehow formed from orientations. And also when you think about text is basically just a collection of different edges oriented differently. So these are two very low-level ideas about what could be of importance to the visual system when we talk about where humans focus. Then more like in a more high-level perspective, you can say that faces or objects could be the most important things, because humans want to interact with the real world, and for this, faces are of importance, in this case, like the penguin's faces, or also, of course, objects, because objects give us a lot of opportunities to interact with the world. So this would be somehow very intuitive, and also, I think you would agree that these are things that you focus on when you explore a visual scene. And then as a special case of this, it's also proposed that especially human faces are very important for drawing your attention, because already as a child we learn, okay, the face of my mother is very important to me because she feeds me and she kind of helps me to manage my life and to develop, and so this would be also like a very likely candidate. So now looking at some experimental results. So these are like data points that were collected from an eye tracking study. So we see basically that the observer focuses on the penguin's faces mostly, but also on the camera in the background a bit more, and also on the human face in the background, but there's still like a lot of noise as well and some exploration in the fixations. So from this kind of data alone, it's very hard to find what are the important features in the end that contribute to drawing our attention. So yeah, already with the beginning of like this research in this area, people were already quite interested in finding models as well, because models might solve this problem because they give us a way to better understand how this data was generated. So when we want to, for example, frame a model, we could think of it like that. So we have an input image, and there's a mysterious processing going on, represented here by this black box. And in the end, we come up with a saliency map. And this idea of a saliency map is very interesting. So is everyone familiar with the term saliency? Or who's not familiar with it? Okay, very good. So saliency is just this idea of evoking a high attentional response from you. So, for example, when you are looking at this scene here at the moment, when your attention is like focused on me or the screen, these are the regions where saliency is very high in a visual scene. So saliency captures where you kind of direct your attention to. And it's not only in visual input, but saliency also applies to other domains. For example, in sound, when you are listening to a tune, you somehow kind of have these moments that you are very focused when a specific, I don't know, like a beat kicks in or something. And this is then a moment where you have a high saliency. So it's somehow like linked to a high probability of really being very conscious about what you are experiencing. And this idea of a saliency map is very neat because the saliency map is basically a 2D probability density over your input image in this case, which tells you that at regions with a high probability density, you have a high saliency. So these are regions where you are very likely to attend to. So in this example, this would be mainly the faces again of these performers. And yeah, so this seems to be most important. And this map was constructed from eye fixations. So how do we come up with a model in this case now? So all that we have is like an input image, and we have the fixations that we get from eye tracking. And with this setting, we now try to find a model that can somehow shed some light on this black box scenario. And since I am not the first person to think about this, there's a zoo of models. In this comparative study here by Kimmerer et al., they compare like a lot of like very classic models that were proposed in the past. And just to kind of make sure you understand how I'm presenting this here. So the gold standard, you can see here, is the perfect model. So what we are measuring here is the information gain explained. So it's basically just how much information are we able to explain with our model given our fixation. So the fixations are recorded, and now we try to find out how much of these recorded fixations can we explain with our model. And this gold standard is our reference, so it's like all the fixations that we recorded. So this has like explains 100%, so all of the information. And you could see this as like the brain model, because the brain somehow generated the fixations that we recorded then in the end. And now looking at all the other models, we can first of all see that there's really not a lot of models that are very good at this task. So at most we reach performance of like 33%, so there's still like a lot of improvement to be done to really have a good model for this task. And one of like the oldest model that was proposed, or one of the very classic models, is this Etienne-Koch model. And what they use is they only use very low-level information. So they make use of color contrast, they make use of orientation contrast, so they take edges, and they look at intensity contrast. And they use these features to predict the saliency map in the end. So it's only very like basic information, but there's been like always a very strong debate about what kind of draws our attention. Is it more like low-level information, like do we look at lights mainly, or do we like attend like edges and our like gaze follows an edge only, or is it like color that mainly draws our attention, or is it more like these high-level concepts? Are we mainly looking at objects, at faces, at people, and these kind of things? And like these kind of models here, so more to the left, we have these low-level models, and then the more we move to the right, people try to include more high-level information. So for example, in this JUT model here, they use like handcrafted face detectors to incorporate high-level features. But it's not so easy to include these high-level features, because you would need like an object extractor for every possible object in the world, so it's not so easy. But luckily, we are in the hype of deep learning. So what you can make use of is you can use filters that you were pre-trained on an object classification task, and use these like filters to extract features that you would use then for saliency prediction. So it's this idea of transfer learning that is applied here. And with these type of models, saliency performance is really boosted. So now we actually have models that are quite good at capturing our experimental data. And like in the following, and in the rest of the talk, I'm going to go deeper into this debate about low versus high level, and I try to come up with like a new low-level model. Because what's very interesting is that more recently people found a new low-level model, which I'm showing here. So it only uses intensity information. It's the intensity contrast feature model, and it outperforms all of the older models, even these that included high-level like faces and these kinds of things. So it again kind of shifted the whole debate on like low versus high-level features, and changed like and kind of stirred the whole discussion up again. So what I'm trying like to find out again, and what was like part of my master thesis basically, is to find the features that drive saliency. That's like the main motivation. But then also I try to disentangle like how much information can we explain by low-level versus high-level information. And then also I'm trying to come up with a new model which we can further reduce this performance gap between this deep case model using object classification, deep features, and the simple intensity features. So looking at methods, I'm going to introduce the architecture that we are using, and it looks like this. So we have an input image, and what we do first is we want to extract features, of course. So for now, we just think of it as a black box again. So we have some feature extraction algorithm, which then gives us a set of feature maps. And then since we have a set of feature maps, we now need to somehow reduce the dimensionality, because we want to have like one probability density over our image, such that we can say, okay, this is a region of high probability. And in order to do that, we propose a readout network, and this readout network recombines these feature maps. It's a 4-layer convolutional network, and we end up with a raw saliency map here. And this raw saliency map is then blurred, so it's very like standard saliency research processing then, and you can add a task-specific bias, because what has been found over the decades is that people tend to focus on the center of the visual field and neglect what's at the boundaries. So you can include this already as a bias in your model, such that your model doesn't need to learn it like a heavy lifted by itself. And then, since we are interested in the probability density, we apply a softmax to end up with a probability density. So that's the basic architecture. I hope I explained it clearly. If not, let me know. So now next we need some models with which we can extract features. So first of all, I'm again showing the intensity contrast feature model. And what we are doing here basically is just blurring the image with different blur kernels. So it's like Gaussians of different sizes, and we just apply them in a like convolutional way and just blur the image with different sizes. So these are like the first features that we're using, and then second, we use also something like we call the variance features, which is the difference between the image before blurring and after blurring. And this again gives us interesting properties and has been found to be beneficial for predicting saliency. So this is the first very low-level model. It's quite surprising actually that it works so well. Then as a second model, we propose this Gabo model. So it's a set of these edge detectors that are parameterized. So during training, we do not only learn the parameters in the readout network, but also the parameters of our Gabo model. And this is just some examples. So what these features, these filters do is they extract edges at different orientation, and we then use these resulting features to, again, as an input to the readout network, which are then used for prediction of the saliency map. So these were both like low-level models. And then, again, as the high-level model, I'm showing here the deep case model, which was like the best model, very much to the right before. And yeah, I'm just showing like a few of these like very high-level features. So I think you've all seen them probably. So it's very like specific, very high-level information, and it's very object-specific. And And it's not only like these few filters, but it's actually like 2,500 features that we're extracting from convolutional layer 5 from an VGG19 net that we trained on the ImageNet task. So then, of course, we end up with a very large number of feature maps. There's like 2,500 feature maps that we then use. So this kind of setting has a lot of more parameters in the end, which also has the problem that we don't really understand of what is of importance in the end. With the previous models, we knew, okay, we are using edges or we are using like intensity values, but here, like, we have 2,500 features, and we don't really know, okay, is it like this filter that encodes a gorilla, for example, that was important for this scene, or is it more a feature that encodes for like some specific structure capturing like leaves on the floor or something like this. So it's very like unclear in the end what the model does, but it does it very well. Okay, so now we need to train our model, of course. And in saliency, we are very much confronted with the problem that eye tracking is very costly. I'm not sure if you have participated, but it's kind of very like hard somehow to sit there, to look at images, to record the data. And then since we train like deep networks here, we need to have a large amount of data. And to solve this problem, luckily there's this data set called Salicon. And what people found here is they use an approximation to eye tracking, basically. So it's not eye tracking experiments that they conducted, but they conducted something more simple, and it's called mouse tracking. So they just show images to subjects in a like Amazon Mechanical Turk setting, and people were just asked to explore the visual scene with their mouse tracking, and at the position where the mouse would be at a certain moment in time, this image would become more clear then. And they found that this very nicely correlates with actual eye tracking data. So this kind of data is not what we actually are interested in, but we can use it as an approximation. And then like this is used for pre-training, and then for fine-tuning, we use an actual saliency eye tracking data set. So you can see the fixations look slightly different, but they still correlate. And yeah, it's 1,000 images only, so it wouldn't be sufficient to train the full network using only these, but for fine-tuning, it's enough. And both of these data sets consist of natural scenes, so it's very like widespread photos of like food and people and parties, and it's very funny actually to go through them, so I highly recommend it. And on this test data set here, or the MIT data set, there's also some of these very artificial stimuli that I talked about before. So next, then we need to train our network, and for this we use this pipeline. So first of all, we need to pre-train our parameters using this like approximated data set Salicon, and we stop the training as soon as the performance on our evaluation data set decreases. And with these parameters, we then initialize our fine-tuning, which we do in a 5-fold cross-validated manner. So we always leave one set out and use it for testing afterwards. And then the loss function we're applying is basically just the maximum likelihood estimator. So we want to optimize our parameters such that they best capture the experimentally observed data. And so this is just the sum over all the images of the log likelihood function. And this probability here, this P of x, y given I, is what our model outputs. So this is the saliency map, basically. Okay, so now finally to some results. So first of all, the way I'm presenting the results. So what we are looking at here is the scale is bits per fixation, so it's some kind of measure of how much information can we explain. So again, we have as an upper bound to the performance that we can expect is this experimental gold standard. So this is the model which could explain all what we observed what we could explain experimentally. So it's at about 2.1 bits per fixation. And then as a lower bound, we use a model which is not really a model, but it's only applying the center bias. So this model only predicts the center bias for every image. So it doesn't really care what image it sees. It always predicts the same. And already with the simple setting, we capture quite some information in our data, and it's about at like 0.9 bits per fixation. And then, yeah, first of all, I reproduced the results. So this intensity model and this deep gaze model set somehow like the lower and higher bound that I'm exploring in between. And I did this with the proposed Gabo model from before. So intensity again is the low-level model, which uses very simple features, and the deep gaze model is the very high-level object focused model. So the Gabo model, we now actually could show that it kind of again decreases this gap in between high and low-level models. So using orientation is very beneficial actually for predicting where humans attend in a visual scene. So this is quite nice. So this again kind of brings evidence for the importance of low-level information and kind of decreases somehow the very big influence of high-level information. And then I think quite intuitively, as a next step, we tested combining both low-level models to see if intensity and orientation would further improve performance, but we found that this is not the case. So this is interesting in a way because it suggests that the Gabo model approximates these intensity features during training. So basically, the Gabo model is the best we can do at the moment with it, if we only want to use low-level information. Exactly. So now I think now that you've made it through this slightly statistical part, I'm actually want to show you the predictions that our models are making. So on the left, I'm showing you the input image that we fed into the model, and then from left to right, I am presenting the results for the Etienne-Koch model. So this was this very early first saliency model. Then there's this intensity model, the ICF, then the Gabo model, and to the very right, there's the deep gaze model. And the higher this number here, it's again this bits per fixation, so how much information can we explain. So the higher this number, the better this is. So first of all, looking at this phase, so this is in red, we see the experimentally observed data. And then as we go through the model, we see, first of all, that this Etienne-Koch model is quite bad at doing this task, which is a bit sad because they are somehow the founding fathers of the whole field, but it is what it is. And then looking at the other models, they all seem to perform similarly, although they focus on different regions of the image. So when we see this very deep blue regions, this is where the model predicts a high probability of you looking at this image, whereas the yellow regions seem to be unimportant to us. Now another example, this you've seen before, and now I'm comparing it here. So deep gaze is very good at only focusing on these faces, and thereby actually captures what is observed in real experiments. Whereas the other models, especially Gabo and intensity, focus way too much on the color contrast in their wardrobe, and they also overestimate generally these light spots that are on these shiny belts here. And so yeah, only deep gaze is really able to capture the experimental results here. Another example, and this is one nice example where the Gabo model actually is best. So we found that the Gabo model is really good at picking up perspective. So we found that when we look at an image with a perspective, we tend to look along the visual axis. And this is something that the Gabo model is very good at capturing. Whereas deep gaze here only focuses on, so there are some pedestrians walking on the sidewalk, and there's some text on this building, but it doesn't really capture this looking along an axis. I think you've all experienced this somehow. And again, Etienne-Koch is unfortunately quite bad. Then one of these very artificial stimuli that were very important for the development of the field. So here actually Etienne-Koch isn't the worst model for once. It's the second worst only, which is great. And this is mainly the case because Etienne-Koch were motivated by these artificial stimuli when they designed their model. And all the other models seem to be way better at capturing natural images. So this is another important insight here. And yeah, this is basically all the predictions I wanted to show you. So with my summary, I want to kind of really make sure that you understand that humans tend to look at faces, at text, and at objects, but they also focus a lot on like low-level feature contrast, so at color contrast, at orientation contrast, you saw that in the stimuli before, and also at intensity contrast. So we do look at lights. And then second, saliency seems to be driven both by high and low-level features, which is also quite interesting because people really believe that you could explain most of it by either one or the other. And really, if you want to like kind of make use of like these predictive saliency models, these classic models perform quite poorly. So if you are actually interested in making some good predictions for your use case, you should think about using these more recent models like deep gaze, for example. And yeah, with that, so if you want to get more into the field, I kind of put the sources here and also some links. So on this web page here, you can upload your own images and see what are the salient regions. So you can like check your Instagram photos before you upload if they are focusing on the right spots. So there's like a toolbox as well that you can make use of. This is from my supervisor. And I also am uploading my code, but it's still work in progress. So yeah, that's all I wanted to tell you. Thanks for listening. And yeah, please ask me anything you want to.
All right, thank you very much. Any questions?
Yeah, thanks for the great talk. I actually have two questions, if that's okay.
Feel free.
So the first one is, because you showed that deep gaze is actually not very good with these perspective images.
Yeah.
Were they part of the training set of deep gaze, actually?
Yeah,
okay.
yeah, of course. So like we had like, yeah, pretty much, there are like, I think 8 to 10 different classes. But they are all part both of training and testing.
Ah, okay. So
yeah.
it actually should know that.
Yeah, but yeah, just since it uses like these filters from object classification networks, it doesn't. There's like I think no class perspective or like look along a street or something. Maybe like in streets, I'm not sure if there's like labeled object street in the data set. I don't know.
So I don't know. This question now just popped into my head. What happened, for instance, if you don't look like at the whole saliency map, but let's say the saliency map of the first couple of 10, 20 milliseconds, is then maybe their low-level features are more important because like the brain processing of like faces and everything didn't kick in yet? Is that
very well, Robert? Yeah, this is indeed the case. So actually this low-level like intensity, this ICF model we tested at least, is way better in the early like first 100 to 200 milliseconds, and then later deep gaze takes over.
Ah, cool.
So yeah, we did find that.
Thanks.
Hi, thanks for the talk. If I understood correctly, you are using this deep gaze is using a pre-trained network and it's pre-trained on object recognition, right? Just with a couple of images you showed, I had the impression that it's a bit maybe biased by high level, like for the face and for this picture with the performers, and it's so I have my question is, have you tried like training a network from scratch with the input data to compare with the ICF and Grabber?
Yeah, the problem is it just really doesn't converge because it's like we have like 10,000 images for pre-training and 1,000 for testing, so it's like 11,000 samples, and it's not enough like to train a network from scratch. I think what people have proposed is to use like random filters, and this kind of so just randomly initializing convolutional filters and then seeing if they pick up some structure in your input images. But this didn't seem to work too well, so it's still, deep gaze outperformed even by a large margin. So yeah, it's a problem because the data that we have access to is very limited. So yeah, we're still, I think if we would have more data, it would be possible probably to do that. I thought, for example, also about like maybe just put on like, I think by now we do have these eye fixation goggles that we can walk around with, I guess, and just use them somehow as the input and then train a network from scratch by using these fixations that you can record at the same time. I think this could be a way to do that because then we have like unlimited training cases basically.
Yeah, I would try like something like data augmentation, or there is also like there is a new data set published in Nature Neuroscience from the University of Osnabrück that released a
yeah,
lot
yeah.
of.
That's very
data.
recent, yeah.
That's very, yeah, like
we haven't included
2 months
it yet.
ago or something
Yeah,
like this.
exactly. Yeah.
Because my impression is that it would be possible to have better results training a network from scratch that is not biased by a object recognition network, because.
I think this is also like the way, I guess, when like a baby learns to understand what an object is, I guess they first need to like look at the object and then learn the label somehow.
Yeah.
So this kind of seems more natural as well. Yeah, I agree on that, but it's not possible yet.
Okay, thank you.
Yeah.
And so that deep gaze too was trained also on web pages, or?
We didn't specifically include like web pages. It's not like what I think we're interested in, but you could of course do that. But you would need to have like the eye fixations as well. So if you want to train your model, you always need like the input image and also like fixations from some study. So I guess if you would have that, then it's like quite easy, I think.
There are no available data sets with web pages.
I haven't checked actually. I guess so when there are these kind of things, then people do it for their own company and probably don't really release it. I'm not sure if anyone knows of them. Please let me know, but I haven't found any. Thank you.
Could you do a meta model which takes the three and train them as a linear combination and then maybe improve even more?
Yeah, I think we've been discussing that. So actually, it would be quite nice. The only thing I did so far is like combining the deep gaze features with the intensity features. But this didn't really improve performance somehow. So I guess it's mainly because deep gaze also learns to approximate these low-level things at some point from high-level features. But yeah, it's really hard to get that out of the model in the end. So it's hard to disentangle.
Any more questions? All right, well, thank you very much.
Thank you.